Greetings and welcome. This is it. This is the moment you have all been waiting for. We are finally digging into algebra and algebraic expressions. As you know, this is going to be a pretty foundational chapter for a lot of your future math classes, and so we're going to start out and really get at the nuts and bolts of what is an algebraic expression, and then what are some really precise terms that we can use when describing these parts of algebraic expressions. So first off, an algebraic expression is just a mathematical expression involving at least one of the four operations: addition, subtraction, multiplication, or division, or more than one of them, and then one of the terms must be a variable. So in this expression, you need to have one of the four operations, a constant, and a variable. These are often used to model real-life scenarios that contain unknown values. So we'll get into more. I just want to briefly touch on this, and then we'll look at more of what each of these means. And algebraic expressions can be used to explore and express the relationship between two values and quantities, especially when one of them is unknown. So you might be wondering, there's a couple words in there. Term is something that we're going to be talking a lot about. It's the quantities or values that make up an expression. So even in something as simple as 4 plus 4, these are both terms, but this would not be considered an algebraic expression because we have numbers as both of our terms. If it was something like 4 plus x, that would be an algebraic expression because this is a mathematical expression involving one of the four operations, and one term is a variable. So the terms can be variables or they can be constants. So in this case, x is our variable. 4 would be considered a constant. So a variable is a letter in an expression that represents an unknown quantity or a quantity that can change. So depending on the problem that you're solving, the value of x could change. Where if it's something like Mr. Plaska had 4 cookies and then he got 2 more, the value of x would be 2. Or I could get 6 more or 10 more. So note that that variable, the value of the variable, can change, and we can make it in an expression kind of whatever we want that fits our problem. And as you notice in this example with the cookies, 4 is called a constant because its value is constant. There is no situation where the value of 4 is going to be different than 4. Its value remains constant. So a coefficient is the number before a variable that is used to multiply it. Later on, we're going to get to something where you might see, for example, like 3b. b is our variable, and 3 would be the coefficient. And you would read that as 3b. And one other little nuts and bolts thing, an expression versus an equation. An expression is a combination of constants, or numbers, and variables, where it's just something like up above, 4 plus x. That's an expression. 4 more than x. An equation combines two expressions with an equal sign, or it's an expression with an equal sign and then a constant. So equations state that one expression has an equal value to the other or is the same as the other expression. So we've seen this not with variables where we would say like 3 plus 2, that's an expression. But for it to be an equation, you would need an equal sign. So 3 plus 2 equals 5. So it's a nuanced difference, but it's important either way that we're using precise language as we talk about all of these different mathematical ideas. So getting into it, this first introduction is just going to be how can you interpret different scenarios with algebra, or what do the four operations look like as we build this understanding of writing expressions and equations that involve a variable. So as I go through these, some of them are going to be easier than others to model with drawing or with like a bar model. And so we're going to be looking at how we can visualize these to see, is our answer reasonable or did we do something wrong? So Lily buys some plants. Her friend gives her 2 more plants. How many plants does Lily have now? So we know here's Lily's original amount of plants, and then there's two ways that we could look at this. Lily's plants, and then the ones that she's given. So the gift of plants. We know that the gift of plants is 2. Oops, that was supposed to be a 2. But we don't know how many plants she has now. So this would be a case where, because we don't know the value of how many plants Lily has at first, it just says some, we can assign that a variable. So this is going to be our unknown quantity. And to replace this, because you wouldn't want to say, how many plants does Lily have now? Lily now has some plants plus 2, or some plants plus 2, like that. This here seems like nonsense. So instead of that, we are going to replace that with a variable. And in this case, I'm going to pick the variable p, because it stands for plants, and it's easy enough. So we know that Lily has p plus 2 plants. So this is how we would write an expression for that. Now, if you drew your bar model this way, here's Lily's original amount, p, number of plants. Here's 2 more. That means this whole bar is p plus 2. So depending on the scenario, having 2 bars or 1 bar is going to be easier to model than another. Just a quick note about when you're picking a variable. I'm going to scroll up here. When picking, we typically avoid certain variables. Things like t often we'll try to avoid because it looks pretty similar to a plus sign, or a lowercase l because it looks like a 1, or maybe an uppercase I, but you don't do the lines on the side, again, because it looks like a 1. So there are some that we just typically don't use very often. O, because it looks like a 0. As you can see, I can't think of any more right now off the top of my head. But yeah, there's just some that we don't see quite as often because they would be easily confused with other variables, or with other like mathematical symbols. So when you're picking them, try to pick something reasonable, but that also fits. So if we're looking here at some other examples of writing some algebraic expressions, we are looking at the sum of z and 8. So we can do z plus 8. Now, if you're not sure, one thing that you can always do, especially with addition and subtraction and in these easier ones, is if you assign a value for that and call it 4, and then you think of this as the sum of 4 and 8, you know from all of your years as a mathematician that the sum of 4 and 8 can be rewritten as 4 plus 8. And this becomes really important when we get to subtraction, because you know 4 plus 8 is the same value as 8 plus 4. So the sum of z and 8 can be written both ways. Same thing with adding 6 to y plus 6, or 6 plus y. Now the language that you use when we look at subtraction is going to be pretty important, so we'll keep an eye out for that to see. X more than 3. So we have 3, and we have x more than that. And then 4 more than r. So r plus 4. So addition is pretty straightforward. You could draw pictures of each of these. You have the value of z, you have the value of 8. To find the whole thing, you would do z plus 8. Same thing here. Y plus 6, add 6 to y. So if I'm adding 6 to it, that makes me think I have y and then 6 more. So y plus 6 would give me the total. Now when we move into subtraction, there are 35 students in Mr. Green's class. There are fewer students in Miss Martin's class. How many more students are in Mr. Green's class than Miss Martin's? So I'm going to do a double bar for this one. So we have G and M for Green and Martin. We know that there are 35 students here, and there are more students in, or there are fewer students in Miss Martin's class. How many more students are there? Would be represented by this amount. right there. And so we would need to assign a value. I'm just going to say S for students. So for us to figure that out, according to this situation, we would need to take 35 and subtract S from it to find that difference. Because if we were to try to flip this around, S minus 35 does not quite make sense, because there's not more students in Miss Martin's class, there's more students in Mr. Green's class. Alright, so subtract 3 from A. Ooh, this is where it becomes really important. This language is really going to be pretty tricky, because when we looked up there at addition, we could flip-flop the order. But in subtraction, I don't think that's going to be the same. So to start out, subtract 3 from A. If I say that this is, let's say, 10, if I'm subtracting 3 from 10, I know that I would need to do 10 minus 3, because I'm subtracting this 3 from that 10. So now if I think about this with that variable A in there, I know that A minus 3 is what we're going to be looking for. And I'm going to quick draw a bar model. So this is A, and if we're subtracting 3 from A, we're taking away that much, and that is 3, and this piece here is A minus 3. So that matches what we found there. Subtract B from 7. So that means I'm taking B away from 7. So if I have 7, and I'm crossing out B of them, what is remaining is going to be 7 minus that B. So if you notice, these are two different scenarios. Here we have our constant first, and then our variable. We're taking away our constant from the variable. So we took away our constant of 3 from our variable. Now, in the second example, we have our variable of B, and we're taking the variable away from the constant, which was our 7. So those ones are pretty straightforward there, but when we look at the less than language, this is where it can be a little bit more difficult. 1 less than m. So I'm going to quick draw this out. And is it going to be m less than 1 or 1 less than m? It sounds like I'm starting out with m, and I'm doing 1 less than it. Or if this was a number line, here's where m is. This place that we're looking for is 1 less than it. So this is going to be m minus 1. So even though our constant is given first, our expression needs to have that variable first, because we are having 1 less than that. We started with m, and we're taking away from that. Next example, n less than 10. So we're starting at 10, and we are going less than that, whatever the value of n is. Or we have 10 in our bar model, we're crossing out n of it, and to get the remaining piece, we would have to do our 10 minus n. So over here, I forgot to put this in. This would be m minus 1. So at first, drawing the bar model can be helpful. Not always going to be necessary as you get more and more comfortable with it, but definitely being able to picture and visualize. What do I have? What am I taking away from it? It's going to be really important. Now when we look at multiplication, Martina has 4 moving boxes. She packs an equal number of sweaters into each box. How many sweaters does she pack? So here's 1 moving box, 2 moving boxes, and 4 moving boxes. So she's packing an equal number of sweaters. I'm going to make our variable s. So in here we have s, 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 and s. So to find our total, we have s 4 times. Now, when I'm writing this, I'm going to have to be very careful. Maybe s is not a great variable because it can look a lot like a 5, but s times 4. So how many sweaters does she pack? Well, it depends. If she puts 2 in each of these, she would do 2 times 4, which equals 8. So that seems to fit with our expression here of s times 4. Now, an important note about multiplication is that s times 4, or 4 times s, you can use the dots or you can use the multiplication sign. that is going to be the same thing as 4s. And so we would read this as 4s, but it has the value of 4 times s. So this is where, if you remember back at the beginning, whoop, whoop, all the way up to the top, a coefficient is the number before a variable that is used to multiply it. So in this problem here with the sweaters, we have 4s is our expression, and that just means that we would have to do s times 4. So notice, subtraction, we could not flip-flop the order. m minus 1 and 1 minus m are very different. Addition we could, and here we are again with multiplication, where s times 4 is the same as 4 times s, and that is a-okay. But regardless of how you write this, it's going to be the same as 4s. So 6 groups of k would be 6 groups of k, or 6k. So the 6 groups of k, I could do a picture. Here's this, and that's a k, and we would have that 6 times. In this case, you know what? I will draw it out because we've got it, so we might as well. 6 isn't too bad, but you could then see that we have k 6 times. The product of b and 5. So b times 5 is 5b. There's your answer. Multiply 4 by w. 4 times w equals 4w. So now you might start noticing using the dot for multiplication a lot more often. That way you can tell when like this times sign is different than the variable x, because x is a very common variable. So typically, if you're picking x, you're going to use a dot for multiplication. All right, so now we get into division. Together, Adam and Elena collected some seashells at the beach. They shared the shells equally. How many shells did each of them receive? So here is their total number of shells. And I'm going to call that B for beach. And how many shells did each of them receive? Well, we would need to divide this up into, so Adam and Anya. I think I maybe called her the wrong name. So that means Adam would get B divided by 2. And so would Anya. So each of them received B divided by 2 shells. Now, division can be one of the more complicated parts with algebra and algebraic expressions. So hang on tight. Here we go. This is a big deal, and it's going to require you to think a lot about the math that's going on and what this language, the language and how that connects all of this together. So if you know that you could read this as half of b, that means b divided by 2 is the same as b times 1/2. Because that's how you would find half of b, 1/2 of b, or half of b. These so far are all the same. Now, if I were to multiply this, and I'm imagining that's a b over 1, I would end up with b over 2. So that is to say that all 4 of these expressions are equal, and they mean the same thing. So it is really important that you're able to look at an expression and see that if it's like c over 7, that is the same thing as 1/7 times c. I'm going to use the dots. 1/7 times c, or c divided by 7. And this to here is very straightforward because we know our numerator over our denominator is the same as the numerator divided by the denominator. So that's something that we've seen before. It's just a little bit of a different application. So keep in mind, those 3 are all the same things. And as you're solving, which is going to be another video in the future, you will need to be able to differentiate and manipulate and use those 3 equivalent expressions interchangeably. So if we're looking here at divide n by 9, that means I am taking n and I'm dividing it by 9. So that is the same. Or n over 9 would be the same way of writing that. Now dividing 9 by n, 9 divided by n is equivalent to 9 over n. So this gets to be really tricky, or gets to be, I don't know, really tricky, but it just takes a moment of like thinking, and what do I recognize? How is this related when you get into mixed operations or multi-step problems? So the order of operations remains the same, and that will be key throughout all of this. In this scenario, Mr. Plaskett baked some cookies. He ate 5 of them and froze 1/3 of what remained. How many cookies did he put in the freezer? So you have to think, what did he do first, and then what did he do? So in this situation, Mr. Plaskett first ate 5 of them and then froze what was left over, 1/3 of what was left over. So if here's all of the cookies that I bought, first I ate 5 of them. I'm going to use C for cookies. So I ate 5 of them, and then in my next step, I froze 1/3 of them. And I need to know this value right here. What is that value? So to figure this out, let's start out with what we had. I know that I had C number of cookies, and then I ate 5 of them. So that shows this first step here. I started out with an amount, I ate 5 of them, so I have some that are less. Now, whatever is remaining, or whatever answer I get from doing this first, I need to divide it by 3. So if you notice, I did put that in parentheses because I wanted to make sure that I do this first. Because I'm not freezing 1/3 of them and then eating 5. I'm eating 5 and then taking what's left over and then freezing 1/3 of them. So you could write this as C minus 5 over 3. Would be the same thing, an equivalent expression there. So you really got to pay close attention and identify what happened first and then what happened next. Now, depending on when you go to simplify or evaluate the expression, one of these two forms, either form A, we'll call this, or form B, will be more useful, and it just depends on what you're thinking about. So next, let's see. Here's 3 other examples that are a little bit, or another opportunity for us to practice this. So first, let's identify what happens first, and then what do you do? So we are dividing the sum of R and 11 by 4. So I know it says divide first, but before I'm dividing, I need to do some addition. So I'm adding R and 11 and then dividing it by 4. Or I could have written that R plus 11 divided by 4. Those are both equivalent. This top one, I would say, is the more common or more accepted form of expressing that relationship. A number that is 7 more than 3 times x. So we need to do 3 times x. Notice how if I would have written 3x, like that just seems a little bit strange. So 3 times x plus 7. Ooh, I remember from our multiplication one that this can be simplified to 3x, those have the same value, plus 7. So when in doubt, try to simplify it just a little bit to make it a little bit easier to write out there. Subtract 4 from the quotient of m divided by 7. So, I have to do some division. So I'm subtracting 4 from the quotient of m divided by 7. I know I'm doing m divided by 7. M divided by 7. I'm going to write it like that. And now am I taking that away from 4, or am I taking 4 away from that? It looks like I'm subtracting 4 from that. So I'm going to write that as m over 7 minus 4. So now that we're getting into these algebraic expressions, start recognizing that if you're doing divided by, this is your denominator. Set it up like a denominator. And that will make your expressions just look a lot more more algebraic, I suppose. You could have written this as m divided by 7 minus 4, or you don't even need the parentheses because order of operations would tell you to do the division first. But either of those works. This would be the preferred way of writing it. Oof. So that was a lot, and we're just getting into it. But if you are able to think about these expressions, or to be able to think about these algebraic expressions in these terms, then you should be good to go. Let's see if there's anything I missed from up above. I think we should be good to go. Notice these are all expressions. We haven't gotten into equations yet, but you can see how that will be the next logical step.